Hello everyone, let's continue. So what you see on my screen are nothing but some application software or apps as we call them as, and these are some of the apps that you use in our day-to-day life, and these apps actually run on the laptop, or this is a representation of a chip which is present inside your laptop. So this particular apps runs on this hardware, and the bigger question over here is how does all this happen? Okay, that's the question that we need to answer. I say the instruction set answers these questions to some level, but let us try to look into the bigger picture. So this application software enters into a box called a system software, and system software in turn converts the application program into the binary language. So let's look into the entire flow of the system software. So the major components, there are various levels of, or there are various layers of system software. The major components of the system software which you see over here are operating system, the compiler, and the assembler. The next job is the job of the operating system, which handles a lot of things. It basically handles memories, it handles the IO operations, it allocates memories, and so on. And other part of the operating system is to take this particular app and convert it into its respective assembly language program, and finally to the binary language program, so that it is being understood by the hardware. That's the major operation of the operating system, apart from the regular jobs that it already does. So the way it does is basically the output of the operating system are nothing but small functions in the C++ or the Java language. These are being taken by the respective compiler and converted into instructions. Now these are the instructions that is the core of this particular course. The syntax of this particular instructions depends upon what kind of this hardware is. For example, if this hardware belongs to, let's say, Intel x86, the instructions will belong to Intel x86. For example, if this hardware belongs to ARM, the instructions will be in the ARM format or the ARM format. If this particular hardware belongs to MIPS, so this particular instructions will have a syntax of MIPS of the MIPS instruction set. But in this case, let's stick to the RISC-V. If this hardware belonged to a RISC-V CPU core, then the instructions over here will be in the RISC-V format. That's the job of the compiler to convert the respective C programs into its to convert the incoming C programs into its respective language or into its respective instructions. That's what the .exe file consists of. Okay, so that's a very important task that this particular compiler does, converting the inputs. The input could be in any input has got a standard format, which is either in one of these particular languages. The output of the compiler is dependent on the hardware, which is nothing but the instructions that is being implemented by this particular hardware. So accordingly, the compiler will convert the output into the respective instructions, and that's the .exe file. And once you have this particular instructions, the job of the assembler is to take this particular instructions and convert it into its respective binary numbers. So this is basically called as a machine language program. The name is quite self-explanatory. Basically, this is the language that the machine understands. It's basically logic 1 and logic 0. If you take up any of my courses in the past, it understands. I've talked about flip-flops and logic gates. They understand only two languages, only two binary digits, that is logic 1 and logic 0. And that's the job of the assembler, to convert the instructions to the respective binary language. And these binary language are being then fed to the hardware, and the hardware understands that if it receives this kind of pattern, it has to do some X function. If it receives this pattern, it has to do some Y function, and accordingly it generates the output. Okay, so that's the flow. That's how it goes from the OS right to the compiler and the assembler, and then to the hardware. That's the entire flow. So let's take a small example over here. For example, if you take an example of a stopwatch app, which if you play over here, it will start the watch, and once you stop over here, it will stop yours. That's a stopwatch app. The output of the OS for this particular stopwatch app could be something like this: a small C function. It could be one of the functions that implements the entire big stopwatch app. So one of the functions is what you see over here. This input, this is in the C language, which enters into the compiler, and the output of the compiler is nothing but, let's say this hardware belong to x86, it will be the instructions, the output instructions of the compiler will be in the x86 language. But in this case, since the course is on RISC-V, let's stick to the RISC-V hardware. So let's say this hardware was an implemented version of the RISC-V instruction set. So the output of the compiler will be RISC-V instructions. Okay, so this is the RISC-V instructions, which is the output of the compiler, and the output of the assembler, which is this particular thing goes as an input to the assembler. The output of the assembler will be over here. It shows an hexadecimal numbers, but once it gets converted into its binary digits, the output of the assembler will be the binary numbers which enters into your hardware. So in a general terms, this particular binary numbers enter into your chip or enter into your chip layout, and accordingly the functions are getting performed over here, and you will see the stopwatch behaving in the way it is expected to behave. Okay, that's the overall behavior of how does a small app, just like a stopwatch app, can work. It is this particular flow. So in this particular course we are mostly focusing on the RISC-V architecture, but in order to understand the RISC-V instruction set architecture, there are various terms that we need to understand inside the architecture itself. We'll get back to that in a minute from now. First of all, let us try to expand this entire C program. So this is the input of the compiler, this is the output of the compiler, and what you see over here, the hexadecimal numbers are the output of the assembler, and this is the core of our course. We're going to go deep into the instructions that you see over here. That's the core of this particular course. Let's try to expand things a bit more over here. These instructions that you see over here, that's nothing but acts as an interface it acts as an abstract interface between the C language and the hardware. So this abstract interface, which is nothing but the instructions, is called as the instruction set architecture. Okay, or generally the architecture of the computer. So this basically represents your hardware. This is basically the architecture of your laptop or of your computer. So this is the language with which a human or a user speaks to the computer. So that's what it's called, and hence it is called as the architecture of the computer. In this case, it is called as the RISC-V architecture. Okay, so that is about the architecture. If you try to expand this one even more, there is something more to it. So there is one more interface that you need to reach from this point to this point, and that's basically your hardware description language. So your hardware understands only ones and zeros. For example, if this particular binary pattern enters into the hardware, it understands that it has to do something. It has to do a function called as add. It understands that it has to add registers. It has to add the contents inside the registers x10 and x's and put the results back into x's. So that's what this particular binary pattern is getting interpreted by the hardware, and the hardware performs exactly in the same fashion. This might be called as a specification, or this could be called as the output of this is called as the instruction or the output of the compiler. The output of the assembler is the binary pattern. Now we need an RTL or the RTL description language which understands or which implements this particular specifications, this particular add specifications, and that's basically called as the implementation or the RTL implementation of your instruction set. Then this RTL is getting synthesized into your netlist. So basically this, if this is the high level description of your specifications, this is basically synthesized version of this particular RTL. So this is in the form of gates, AND gate, OR gate, inverter, flip-flops, and so on. And finally from this point to this point is generally a physical design implementation of this particular above netlist. Okay, so you start from this instruction set, you try to get the specifications of this instruction set, you write a hardware description language of these instructions, you synthesize it to the gate level, and this gate level is then converted into its respective layout based on the using the general RTL to UTS flow. So this is the part 1, which is RISC-V instruction set architecture. This is the part 1 course. The part 2 course is nothing but the RTL and the synthesis of the RISC-V based CPU core, which is this one. We are going to learn or talk a lot about synthesis concepts over here, and finally we are going to do a physical design implementation of this particular RTL. So those are the 3 different parts of the entire course, and this part 1, or basically part 1A, is nothing but the RISC-V instruction set architecture. So this is the part 1A. Part 1B will be mostly about the application of the RISC-V. So we'll keep it to a separate course. This particular part A will talk about the RISC-V instruction set architecture, or especially the architecture of the RISC-V. So let's stop at this point and let's begin with the contents of this particular course in the next video. Thank you.